Moving on to the functional modeling, what are the tools for functional models in constructing the human environment systems? There are many ways to build functional models in human environment systems. Jackson specifies 4 incremental tools for modeling systems: causal loop diagramming, system archetypes, stock and flow diagramming, and micro worlds. So these terms are slightly different, and we'll see that in a minute. Stock is like a reservoir and how much of a material or some quantity is there, and flow is like a flux. I think some of you understand the reservoir size and flux better. The two former are qualitative and the two latter are quantitative. So causal loop diagram and system archetypes are qualitative, and of course stock and flow diagramming and micro worlds have to be quantitative. The basic building blocks for constructing functional models in human environment systems are again elements and dependencies. However, this time the elements are variables that can change, and dependencies between elements are directional and can be either positive or negative. So you can have increasing or decreasing dependencies between elements. These dependencies cause a change in one element to spread to associated elements, creating a branching chain of causal relations through which any impact in the system could propagate to distant parts of it, as these papers indicate. But that's what is meant here as well in this one. And oops, why did I jump? What happened here? I jumped. Oops, I went. What happened here? Okay, so somehow I am jumping around. So that's what happens in this diagram here. We have dependencies indicated by these things, and we have micro worlds and system archetypes. Everything is in here, but we have to think of them in a functional sense. Okay, so that's what we are talking about. So the propagation of God, I'm not doing well today. I had a big party last night, and even though I got good sleep, I'm a bit groggy today. So the propagation of a change between each pair of elements may be immediate or delayed to various degrees, making the time period for analysis important, since the time scale before the appearance of adverse effects is important, and linking risk to sustainable development. So these words can have great meaning when we'll see the example, but we can see the example here very clearly. Did I jump many things from here to here? No, I have read them. Okay, so for example, cryosphere is a very slowly growing system which can melt much more rapidly. With global warming, we are melting things, and that can go very rapidly because of something called ice albedo feedback. If you don't know what that is in this context, don't worry about it, but I have podcasts you can look up. Things in the stratosphere are generally much slower because it's well stratified and moves slowly, whereas troposphere is a fast churning system. Upper ocean is a fast responding system, as opposed to the lower ocean, which is deep and has high inertia, high heat capacity, and so on and so forth. Okay, so you know that human systems are moving fast in terms of consuming fossil fuels and energies and adding greenhouse gases and so on and so forth. So you get the sense that if you change cryosphere, for example, if you melt glaciers, sea level is rising globally, but that is distributed unevenly because of the circulation, the dynamics, and the wind changes and so on and so forth. So that's what is meant by saying they can be delayed impacts, and they can be far and not just local. Okay, so these delays often indicated by two parallel lines crossing the dependencies in causal loop diagrams. So we'll see this book's version of the causal loop in the next slide. So the delays are also major contributors to the complexity of systems. So something may happen and you may not even be aware that you may be aware that it happened, but you may not be aware that its effect is going to come to you with a delay. It is thus not only the number of elements that determine complexity, often referred to as detailed complexity, but also dependencies between elements, leading to what Senge refers to as dynamic complexity by the separation of cause and effect both in space and time. So cryosphere is, let's say, somewhere in the Himalayas or in the Greenland, in Antarctica, Arctic, and so on. So the changes there are going to affect you. Monsoon is being affected by all these things which are far away, and it's not always instantaneous connection. Okay, so chains of causal relations sometimes create loops, so-called causal loops, feeding back to the propagating changes to elements earlier in the chains. So we will see that also. Such causal loops are prevalent in our world and are yet another source of complexity, as they give rise to non-linear diagrams. So a small perturbation may get amplified or damped depending on how non-linear and how positive and negative the feedbacks may be. So here is an example of a causal loop of elements, directional dependencies, and delays. So there are some factors involved here, alpha and gamma. So if you don't understand, don't worry about it. So the causal loop is going from here alpha perturbation to the element, and it's a positive feedback, so the initial perturbation will be amplified and there can be a delay. So this indicates that it's not instantaneous, but it's delayed, but it's an amplifying effect. And depending on the dependency, the element perturbation affects another factor, variable omega. So that dependency is negative. So if element goes up, this goes down. So that's the negative feedback. And then omega affects other elements with a delay, but here you are getting another positive feedback, and so on. As we said before, you can technically multiply these feedbacks and see that there's only one negative feedback in the system. So this causal loop, if it is really that linear, should be a net negative feedback, in the sense that any perturbation to any part of this system will be damped out in the long run as a overall functioning of this causal loop. Okay, function is important in this case. These causal loops can be either reinforcing or balancing, so that's positive or negative feedback in the network language. A reinforcing causal loop results in either continuous growth or decline in the elements of interest. So initial perturbation keeps getting amplified. Negative doesn't mean it's getting damped. For example, if the glacier starts to melt from global warming, it can very rapidly disappear. So that's a decrease or decline in the glacier mass, but it will be an increase in sea level, and so on. While a balancing causal loop results in stability through dampening or negating changes in the elements in meeting a set target. Okay, so you can imagine now the glacier growing, which has happened in the past during ice ages. If somehow glaciers begin to grow, let's say because of the orbital changes, then as glaciers grow, more sunlight is reflected, it gets colder, and the glacier can continue to grow. So it's also a positive feedback, but in this case the glacier mass is increasing instead of decreasing. It is, however, important to note that growth and decline and stability may all be positive or negative depending on values and perception. So now we are throwing human systems into it as opposed to just ice albedo physical system. Balancing loops that drive systems to meet set targets for specific elements are rather easy to identify, as they attempt to reduce gaps between the actual and the desired state of the elements in question. However, balancing loops without such explicit targets are not always as intuitively obvious to distinguish from reinforcing loops, as this distinction depends on which element one focuses on in the causal loop. it's a bit wordy, but we'll see examples when it will become clearer. So here it is. For example, if one focuses on the element marked by alpha here, alpha is here, omega is here, any change in alpha will continuously reinforce itself, since the change propagating from alpha has the same polarity as the subsequent change coming to alpha. So this is a bit complicated. So before I said this entire loop is negative, but the way element alpha is being interpreted is alpha is changed, it's having a positive impact on the next element, but it's also getting a positive feedback from the loop. So causally speaking, this keeps growing, but here is a negative in here, so this tends to damp omega, but omega then damps the next element and so on. Amplifies the next element and so on. So don't worry too much about it. Just get a sense of the positive and negative feedbacks with the thermostat example I used, or the isolvedo feedback examples. If one focuses on the element marked by omega, on the other hand, any change in omega will be dampened, as changes propagating from omega has an opposite polarity to the subsequent change coming. So let's leave that there and move on to human environment systems, in terms of constructing with these structural and functional models. When constructing qualitative models using causal loop diagramming, for which the output is a more or less complex system of causal loops, so in the real world, as we saw with the Earth system diagram, there is not just one causal loop, there are multiple interconnected, interdependent causal loops. So it is at times possible to identify system archetypes. A system's archetype is a pattern of behavior of a system based on a set of elements and dependencies in a functional model, which can be found in various contexts and can thus be generalized and used to analyze systems behavior or guide the construction of human environment systems more generally. So let's leave the words there and then we'll come back. Examples of such systems archetypes that have been applied in many contexts are limits to growth. So as it goes back to the 1970s, and then the planetary boundary layer idea, planetary boundaries idea from Rockström that started in 2009, tell you that we cannot keep using fertilizer and keep burning fossil fuel and so on, and keep doing agriculture without hitting the limits of the planetary functioning itself. So the planetary functioning will collapse in terms of nitrogen cycle perturbations and its impacts on soils and ecosystems on land and ocean and so on. And of course, if we keep burning fossil fuels, we're going to keep increasing greenhouse gases. Global warming will increase, and then sea levels will rise because glaciers will melt, cities will disappear, it will become too hot to grow crops in some places, and so on and so forth. Or shifting the burden example, or the tragedy of the commons. So this requires a little bit more care. Hardin in 1968 started this big debate about tragedy of the commons, but the example he used, I have discussed this elsewhere and we'll discuss it again in the context of the sustaining the commons part of this course from Janssen and Andries that I mentioned many times. Hardin imagined a pasture that is shared by a number of people for grazing their sheep, and there is no limit on how many sheep they can buy and graze, and eventually everybody has too many sheep and you have not enough pasture, so you end up having a tragedy of the commons. So the problem there is commons has a definition that arose many centuries ago, and the way Hardin explained it, that's not a common, that's an open source, open access resource where there are no rules or norms or regulations. People just keep on buying sheep, and then a tragedy of the commons is created. Whereas Ostrom's work has diligently put together cases and design principles about actual commons where you actually have rules, norms, punishments, so that you can avoid tragedies of the commons, and there are examples of communities working together where that has been done. So that's a functional modeling aspect as well that will come back. Okay, so maybe I should leave this here and then come back and continue this idea of functional modeling in the next podcast. This is almost 15 minutes. But try to link the concepts together. Structural modeling and functional modeling in the end are not really independent, because when you do the Earth system and want to include human impacts and climate change impacts on humans, you are combining the functional parts and the structural parts together. Okay, so we'll come back and continue.